So today we're very glad to have Professor Weisen Shen from Department of Geoscience at Stony Brook University. Weisen got his bachelor degree from the University of Science and Technology of China, also known as USTC, which has one of the best geophysics program in China. Weisen's PhD is from University of Colorado, Boulder, and he got his PhD working with Professor Michael Rieswaller, who is a distinguished alumnus of our department. So today, this talk is really a homecoming for Weisen as an offspring of our department. So welcome, Weisen. After getting his PhD, Weisen was a postdoc fellow at Washington University at St. Louis. And after that, he joined the Department of Geoscience and Stony Brook University in 2018. Weisen's research focused on understanding the structure and evolution of the lithosphere with seismic methods. And today, he's going to tell us about his recent discoveries about the crustal composition and the strengths of the Intermountain Seismic Belt. With this, I will pass it on to Weisen.
Thanks, Tianze. Thank you very much for the invitation and the lot of effort to prepare this, to organize the seminar. Although 2 minutes ago, I worry a little bit whether I gain enough audience to match your criteria of 15 audience. And I'm happy that we finally have 15 people, exact 15 people here. So now I can start. As Tianze introduced, I am a seismologist, and I got extensive training to do observational seismology. So in my PhD time, I did a lot of work to just imaging the crust and the uppermost mantle of the continental lithosphere. And today, I want to shift what I have focused on in the past and talk about something that I never touched when I was a PhD, but I got more and more interest in the past 2 years, which is crustal composition. So the title is Crustal Composition and Strength, and a revisit to the Intermountain Seismic Belt. Before I dive into the presentation, I want to give some introduction to the terminologies I listed in the title. So first, the terminology is composition. What do I mean composition here? So in this talk, when I refer to crustal composition, I mainly mean the silica content. If you look at the figure here on the right side, it's just every Geology 101 book has this type of figure that tells you how to classify different rocks. And one major indicator to classify the Earth rock is to use silica content. Basically, for the rock that have lower silica content, people classify them as ultramafic or mafic and mafic rocks. And for the rocks that have higher silica content, people call them felsic rocks. So silica content is a major indicator for different types of rocks. And the silica content is also very useful in many aspects of rock classification because it is correlated with like abundance of heat generation elements. For example, the potassium, more silica, the rock with more silica, it usually comes with higher potassium element concentration. It is also related to the melting temperature and many other physical attributes like density and seismic properties. So in this talk, when I refer to crustal composition, what I mean is the silica content. And with the silica content, there are 3 terminologies I'm going to use frequently in the rest of the talk. In the first one is felsic rock. Felsic rock here, I mean the rocks with silica content with weight % higher than 63. And another one is mafic rock. Mafic rock is this low silica content rock that has SL2 weight percent lower than 53. And the rock that have silica weight percentage between 53 and 63, I call them intermediate rock. And because I'm going to focus on the crustal composition, so I'm not going to include those ultramafic rocks here. Okay, so this is the first terminology, crustal composition. The second terminology is strength. Okay, what do I mean strength? Basically, strength is the capability to deform of any material under given stress. If it does not want to deform a lot, we call that material have a higher strength. And vice versa, if it has a lower strength, it means it tends to deform more under the same stress. And for crustal rocks, people usually use strength profiles. Here I show several strength profiles on the figure, lower left figures here. For different crustal sample. Okay. Those strength profiles, usually they have a brittle regime, which means under this regime, crust usually is elastic under low stress. And once the stress goes to a critical value, it will break. And that's called a brittle regime. Okay, so the green line here on the first figure shows a brittle regime. And usually the greater the depth, it takes a higher strength to break a rock. So you can see this strength curve will increase linearly. And at a certain depth and the temperature, the crustal rocks or rock in general will go into a different deformation law, which is a flow law here. And under this flow law, the rock will deform like a plastically. And this deformation can be described by this equation here. I'm going to explain this equation more later. But the overall pattern is that at a greater depth and a higher temperature, it takes less and less stress to make the crustal rock to deform at a given strain rate. So as a whole, the crustal rock will have a strength profile shown by the red dashed line here. This red dashed line looks like a Christmas tree. So many people call it a Christmas tree diagram that describes the strength of a given crustal 1D profile. And the strength is, it varies as a function of many factors. It can vary with composition. It can vary with confining pressure, temperature, strain rate, and fluid content. Here I show you the example of how the strength profile changes with temperature. On the middle plot, the red curve shows a strength for the geotherm of 15 degrees C per kilometer, which is a relatively colder regime. And if we increase the temperature for this particular type of rock to a higher geotherm, like 30 degrees C per kilometer, the calculated strength profile will be like the blue curve. We can see that the strength of this particular profile will get decreased by the increasing temperature. This is mainly because the T temperature here in this equation then relate the shear stress with a given strain rate. So the general rule is the higher the temperature, lower the strength. Strength is also depends on the composition, particularly for different rock with different compositions. The A, N, and Q, those parameters will change for various rocks. So here I show you the strength profile for different types of rock. One is the dry quartz, it's actually a mineral. And another black curve shows the strength calculated for the dial base, which is a mafic rock. we can see that the diabase will transition from brittle regime to flow regime at a greater depth. And as a result, it takes a higher stress to deform the diabase. And we see that the diabase has a higher strength than the quartz. So this is some clarification for the strength. And the third terminology I'm going to talk, I listed in my title, is Intermountain Seismic Belt. What is the Intermountain Seismic Belt? If we look at the seismic hazard map published by USGS, we quickly notice the strike steep faults in the coastal California. That's the plate boundary. There's another seismicity hazard, high hazard zones in the central US. But another belt shows up here in the Intermountain West region that extends from the Montana to the south across along the boundary between the Idaho and the Wyoming, and then into the Utah. This is a region with also with high seismic hazard, and people coin the term Intermountain Seismic Belt to describe this high seismic hazard zone. And if you look at the seismicity in this region, this is a very early paper published by Smith and Spar in 1974 on the seismicity in this region. They first talk about this Intermountain Seismic Belt in this paper. And we can say if just in the 10-year time window between 1961 and 1970, they have recorded a lot of earthquakes here. So basically this is a belt with a high seismic hazard with a lot of earthquakes. And if you look at the geometry more carefully, we can identify several different arms of the Intermountain Seismic Belt. For example, there is one particular north arm that goes along the northwest direction into northern Montana. And there is a south arm that goes along the Wasatch Front into the southern Utah. So this is the major two arms of the Intermountain Seismic Belt. But in the meanwhile, we can also find a group of seismicity happens in the state of Idaho. Here I call it Idaho arm. It is co-located with the Idaho basilis. And the arm of Idaho and the southern arm they form a very interesting U-shaped pattern that is cut by the Snake River Plains, which has very low seismic hazard, and there's no seismicity in this place. I call it the Snake River Plains quiescence. And this U-shaped area formed by the Idaho arm and the southern arm, the Wasatch Front of the Intermountain Seismic Belt, together with the quiet Snake River Plains, shows a very interesting U-shaped form of this seismic belt. So with those three terminologies defined, the composition, strength, and the Intermountain Seismic Belt, I'm going to talk about our recent investigation to this region. With the central question that drove me at the beginning, why the Intermountain Seismic Belt is in such a geometry, this very interesting U-shaped geometry. Basically, I mean, why do earthquakes happen in those regions where they happen, but not in other regions like Snake River Plain? And to guide you through the talk, I divided it into 5 standard parts. Number 1, I'm going to talk about the tectonic background of this region. I list some existing studies and theories to explain this seismic belt. And then I talk about the new seismic information we collected from USArray and why it matters to this seismic belt. And then I present a key step, then how we quantify the crust composition from those seismic properties we mapped. And finally, I talk about the crust strength map and what new we can learn. And finally, I wrap up the talk with caveats of the study and talk about some potential in the future. Oh, by the way, throughout the talk, please feel free to ask questions when you have any. You can either type your question in the chat, I can read instantaneously, so I can answer instantaneously, or you can just stop me anytime. Okay, so let me talk about the background. What we already know about the Intermountain Seismic Belt. What are the existing theory to explain why earthquakes happen there? There is this very famous classic paper published in 1974. This is quickly right after the development of the plate tectonics theory as well as the plume theory. So in this paper, the authors, Smith and Spar, explain the Intermountain Seismic Belt using the plate tectonics theory. Basically, they say the Intermountain Seismic Belt represent the boundaries between several small microplates. And those microplates are the, for example, the Basin Range microplate, the Northern Rocky Mountain microplate, and they all bounded with the stable Eastern US. So it's a plate boundary. That's why you have earthquakes. Although it didn't say too much about the, it didn't give a explanation to the Idaho branch, where we see the Idaho arm that has a very high strain rate using the plate boundary theory. But they mentioned the possibility of this Snake River Plain, which is a hotspot track, might have impact to the seismicity here. So basically, the first theory is the strain release along the microplates boundaries. There are other theories can potentially talk about explain the seismicity here. There is another category of theory, which is which I show an example here. It's also a paper published by Professor Bob Smith in early 80s. Basically, in this paper, they say there is a, they look at the deformation model here, the rheology model here, and they find that there is a big difference between the strengths of the crust between the Basin Range and the Crustal plateau. They look at the southern arm of the ISB, and they find that this perhaps is related to higher temperature in the Basin Range area, where they call it a thermally deforming continental lithosphere in this area that might play a very important role that can generate earthquake here. Basically, the idea is you have a higher temperature, it's weaker, and then the strain rate will concentrate in that region. So this is a second potential theory. Actually, later in early 2000, Bob Smith and co-authors published another paper concentrating on small regions near the Yellowstone. So in this paper, they look at the gravity data and use the gravity to derive the density of the crust in this region, which includes the Eastern Snake River Plain, the Yellowstone, and the Yellowstone Plateau, which is to the east side. And they find that perhaps the thermal structure here I show you the heat flow, surface heat flow they used in their modeling, perhaps still plays a very important role to lower the strength beneath the Yellowstone caldera. But they also find that there is some hint that the seismic plane might have a different composition. However, they conclude in their paper saying this Yellowstone and the seismic plane quiescence is not resolved by this study. So it's still a mystery why the seismic plane has a very low seismicity. But in conclusion, the previous studies have revealed a weak lithosphere along the microplate boundaries. It's one of the proposals to explain this high seismicity here. Another possibility is that a thermally deforming model, okay, higher temperature will make it weaker. And the composition perhaps can play some role in the seismic plane from gravity modeling, but it does not fully explain why just the seismic plane does not have seismicity, but it's all surrounding regions all have high seismicity. And many of those early studies, they either focus on a small part of the ISB, Intermountain Seismic Belt, or just near the Yellowstone. So it does not cover the full picture. And what I am going to do today is to use the USArray and talk about the strength modeling that we have produced for the whole Intermountain Seismic Belt. And I'm going to show you how we approach it. The way we do this is by mapping the chemical composition using the seismic properties derived from USArray, and also modeling the rheological properties of the crust. Okay, and at this moment, do we have any questions? If not, I'm going to move into next section. Okay, we are good. Okay, also please let me know if I go too fast. Okay, USArray. Some of you might not be familiar with USArray. USArray is a large sweeping network that systematically covers the continental US and Alaska since the year of 2007, 2008. And it's a systematically deployed network with a station spacing about 70 kilometers. Every station will stay there for 2 years and then move to a new site. And this array has allowed the seismologists to produce high quality imaging to the lithosphere beneath the continental US. Here I give you an example. For instance, this is a map of the uppermost P velocity or Pn speed derived by Buehler and Scheer 2 years after the initiation of the USArray. And interestingly, they find the seismic plane has the Yellowstone hotspot tract has a relatively low P velocity in the uppermost mantle, while the rest of the area have a very high velocity. So people might think, okay, this is the supporting evidence for thermally deforming mechanism in this region, except that the high temperature region is corresponding to the low deformation rate region, which is very counterintuitive. There are also other images made by USArray. There are, for example, here I show you a 3D model published in 2016 by me and my advisor, Mike Reiswolder. Basically, in this work, we incorporated different types of seismic measurements, receiver function, surface wave dispersion, and Rayleigh wave H over V ratio to build a 3D model from the surface to about 150 kilometers. One thing I want to draw your attention from this model is that if you look at the middle crust image, which is shown in panel C here, we can easily identify a structural boundary in the crust between this northern Rocky Mountains with the Great Plains, as well as the Eastern Basin Range with the higher speed Colorado Plateau. So apparently this is a seismologically structural boundary that is coincident with the Intermountain Seismic Belt. And in the meanwhile, we also observe a high speed structure beneath the Snake River Plains, which at that time we interpreted as the magmatic intrusion, we have imaged. So what we conclude from this plot is that although the structure perhaps gives us very useful information to tell something about the strength or rheology in this region. Okay. How does it affect the rheology? Why does the seismic information can tell us the rheology? My feeling is that this is because crustal VS is also affected by both temperature and composition. Those are also two factors that affect the rheology, except that there's no simple theoretical relationship between crustal VS and the rheology. And in the meanwhile, it's also difficult to easily derive rheology or strength information from the shear velocity. Here I give you an example. Here, what I plot here is on the x-axis is a shear velocity or Vs, and one on the y-axis is the silica content or chemical composition. So each of those dots and squares, they represent lamp measured rock samples of those two quantities for the crustal, major crustal rocks. And what we can see that although there's a trend showing that usually higher speed is corresponding to lower silica content or mafic rock, and the lower Vs speed have more rock samples on the high silica content side. So there is a weak connection between shear velocity and the silica content. And we know that rock composition has something to do with strength, right? So there is a weak connection between Vs and strength. But this relationship is not one-to-one. For example, if we know that a region has a shear velocity, crustal shear velocity of 3.6 kilometers per second, the silica content can go from 50% to 80%. Those rocks with all different silica content can all have this shear velocity. So this is a problem to just use Vs to tell us something about the composition. But if you look at the colors here, every data sample I color coded by the VP-Vs ratio, we can find that although the rock with the same Vs may have different silica content, but usually the high silica content has a rock with low VP-Vs ratio, while the low silica content has a rock with high VP-Vs ratio. This information is more clearly seen if we replot the data on the left side, rearrange the y-axis and x-axis, except plotting them on Vs and silica content axes. I plot the rock with Vs and VP-Vs ratio, but color code their silica content for each dot. What we find that this is a monotonically changing pattern here. For the rock samples with high Vs and high VP-Vs ratio, usually they are color coded by blue colors, low silica content. And for the rock that have low VP-Vs ratio and low Vs, they are color coded by red color, high silica content. This means if we can determine Vs and VP-Vs ratio at the same time, we can perhaps uniquely determine the average or the most possible silica content for that given place. Okay, so basically this is the major drive, major reasoning that I make to do the next step to relate the seismic property with silica content. Okay, now the question is how do we measure them? For the shear velocity, we already have those shear velocity maps for different depths of crust. But for the VPVS ratio, where can we get them? Again, USArray is a super useful tool. People have produced the VPVS ratio across the United States using USArray. Here is the result from the Earth Scope automatic receiver surveys for years. Basically, the idea is that the technique will take advantage of the multiples of the seismic wave that are converted at MOHO and measure their arrival time and stack their energy with different VPVS ratio and depth choices. When we are hitting the right VPVS ratio and the right MOHO depth, we get the high energy stack. So here I show you an example of M26A station in Denver Basin, somewhere here in Colorado. And this technique determines a VPVS ratio about 2.1 and a crust thickness of about 40 kilometers. 2.1 VPVS ratio. That is a very, very high VPVS ratio for the crust. I think the technique get this very extreme value is because the sedimentary basin can add some extra phases that can delay the MOHO-derived phase and add noise to the data. So as a result, this value may not represent the real VPVS ratio for this particular location. And if we apply this technique to all the stations, we get a very noisy result. So which is shown here on the left side. It's difficult to recognize any systematic trend in the US. So we look at the reasons and we find that perhaps this is related to the sedimentary basin signals. So we tried to do two things with the same technique. Number one, we reselect the events to only retain the high quality receiver functions. And number two, we separate the sediment signal from the MOHO signal and do the energy stacking separately. So for the same station where years gives the VPVS ratio measurement of 2, M26A, we apply this technique and find that the true VPVS ratio beneath this station in the crystalline crust is only 1.83, which is more reasonable value compared with the value of 2. Oh, by the way, this value represents our determination of VPVS ratio for the crystalline crust because we already separated the sediments out. And if we apply the technique to all the USArray stations, we can regenerate the crust VPVS ratio across the continental US. The map is shown here. Now we can recognize some trend. For example, you can see in general, the Western US have the lower VPVS ratio, while the central, stable, cratonic central US has a higher VPVS ratio. And we also recognize some more local features, like the Idaho Basilis has a low VPVS ratio, and the Snake River Plain has higher VPVS ratio. With this map and the VS, now we have both quantities for each station of the USArray. So next step, we can quantify the chemical composition from the two quantities empirically. Okay. So the idea is this. Number one, we have shear velocity for each location of taken out from the 3D model we generated in 2016. Number two, we newly measured the VP-VS ratio for each location because we only measure the average VP-VS ratio. So we take that value as a representative VP-VS ratio for that location. And each of those quantities come with uncertainties. When we measure them, we also estimate our measurement errors. And then we perform a bootstrap technique more precisely. Basically, we take every possible VS profile and all the possible VP-VS ratio measurement and look up for the VP-VS ratio and VS, look up the color here, the silica content for that profile, and then generate a 1D silica content profile for each station. And because we are doing a bootstrapping, so we can generate a lot of silica content profiles for each of the location. Here, the blue curves show you the silica content we obtained from the petrological database for station M26A beneath Denver Basin, derived from the VS profile here and the VP-VS ratio 1.83 here. And if we take all those 1D silica content profiles or possible profiles and integrate their VP-VS ratio and calculate the average silica content within the crust, we can get a distribution like this. On average, beneath M26A, the silica content is about 50% for the crystalline crust rock. We can also do this for another station like F12A beneath basin range. We can also get a 1D silica content model. And then we can get the average bulk silica content for that station. It's about 65%, which is 15% higher than the silica content beneath Denver Basin. Very strong variations beneath the two stations. And if we do this technique for all the stations where we measure both VP-VS ratio and VS, we get a map view like this. This is a bulk crustal average silica content within the crystalline crust for the continental US. And I'm showing you this pattern, but I'm not going into the details of the pattern. We'll talk about this in the next few slides. But my point here is we get those bulk crust average silica content. We can also get a map view for different depths because each location we have 1D silica content profile. So essentially, we have a 3D compositional model. So on the left side, I show you the upper, middle, and the lower crustal silica content, as well as uncertainty measurements. We can also draw transects along different crossing transects to show you how the silica content vary with depths. So basically, it's whatever you can view your 3D seismic model. Now we can view the chemical composition for the United States, the crust. Okay, now you may want to ask the question. It sounds like a very simple technique. You measure the VS, you measure the VP-VS ratio, you take the petrological database and empirically relate them to get the compositional model. Can I trust you? Should I trust you? Right? Is the result reliable? So here I'm going to show you some of the evidence then why we think the result makes sense. Number one, it makes geological sense. For instance, if I look at the Western United States, in the Western United States, people know that from the surface geology, some places have a lot of mafic rock eruptions. For example, the Snake River Plain is a hotspot track where people can collect a lot of mafic volcanism in this place. In the Southern Oregon, Northern California, the high lava plains also has a lot of mafic volcanism. So if we look at the distribution of the mafic volcanism, which is plotted as the blue dots here, we can find a high correlation between the mafic volcanism and the high low silica content we observed for the bulk crust, which means our result, the bulk silica content is consistent with the surface volcanism. Okay. Number two, people can also measure the geochemistry at the depths, but using technique, not from the seismology. Xenonese is the rock sample that people collected from the melt that brought those deep crustal samples to the surface. In some part of the United States, like the Wyoming, central Wyoming, geochemists, like here, Barnhart et al., collected a lot of deep crustal xenonese rock samples. And with those rock samples, they can measure the bulk composition. It can be measured. And in the meanwhile, if they perform thermal barometry data, they can also determine the depths of those where the xenonese is originated. So here I show you the pressure of the samples they measured. So basically, they can determine the bulk composition and the depth at the same time for select places. Now, if we take their samples, there are many samples collected from the 3 sites in central northern Montana, and plot them against the silica content profiles we generated. We can find that their samples is highly consistent with what we observed, we measured from the seismology. I think this perhaps represents the strongest evidence and why we think the 1D profiles of the silica content is giving us some real geological information. And if we look at a greater scale, in 2015, Hanker et al. Compiled a lot of granulite facies xenonese across the globe, published previously. And they compiled the weight percentage silica content for all those granulite facies. Granulite facies rocks are the major constituent of the deep crust. And when we try to compare the deep crust composition we measured from all the United States and compare with their distribution, we also find a high correlation between the 2 independent data sets. Here I show you our result in the red distribution, and the xenonese data collected worldwide is in the blue open distribution. So basically our result is also consistent with the global collected xenonese data. So as a result, perhaps those pictures of the 3D compositional model is reliable and should tell us something about the chemical composition, and in addition, something about the strength. Okay, now I'm going to move to next slide section. Integrate the compositional information into the rheological modeling. Oh, by the way, Tianze, since we start the talk about 10 minutes late, can I keep going?
Sure, yeah, go ahead.
Okay.
Yeah.
Yeah, this is
we don't have a hard limit for the time, so
okay.
You can feel free to finish up.
Okay.
Whenever you want.
Okay, I only have 10 more slides. Okay, I'm going to finish it quickly. Yeah. Okay, so now we have composition. What do we do? Here I'm going to follow what have been done in 1984. In 1984, Bob Smith and co-author model the strengths using some assumed composition and thermal information. And now I'm going to follow what they have done, but using updated composition and updated thermal information. As I said at the beginning of the talk, the strengths, the profile is mainly controlled by composition and temperature. So here I'm going to show you an example. This is station TAL11A. This is in the western side of the Snake River Plain. And if I look at their composition, I find the average composition, all the possible composition profile in this beneath this station shows that for the upper part of the crust is not felsic. However, it is intermediate. And the lower part of the crust is mafic. And we also take the geothermal heat flux, the most recent geothermal heat flux map of the United States, and take the thermal gradient measure at the surface and calculate to the MOHO and get a thermal model. With those two information, we can calculate the stress profile for this location using the information on the left. Specifically, we assume the upper crust is intermediate, and we use a quartz diorite to represent the strength of the crust in this place. And for the crust below 15 kilometers, because the silica content is so low, it's lower than 53%, we use mafic rock, which is diol-based, to represent the strength. And then we can calculate the strength, and if we integrate the strength, we get a number of the crustal strength for this location. The number is 6.56 times 10 to the 6 megapascal kilometer. Okay, this is one station. If we look at the other stations in Snake River Plains, interestingly, we all get similar strength profiles, and their integrated strength is all around 5 to 6 times 10 to the 6 megapascal kilometer. Okay, so maybe we are seeing some structural consistency here. Now, if we take a look at another station, this is a station just maybe 100 kilometers from the first station. Okay, this is the first station. The second station is not very far away, but it's located in Idaho Basilis. And in Idaho Basilis, our compositional model has a very different profile. The upper crust, the upper 20 kilometer, is in a felsic regime, while the lower crust is only intermediate. It never goes into the real mafic regime. And in this place, if we model the strength using granite for the upper crust because it's felsic, and the diorite for the lower crust, we will get a very, very different strength profile compared with the station in Snake River Plain. And the integrated strength here is only 2 times 10 to the 6 megapascal kilometer, instead of being 6 times 10 to the 6. And if we look at the other stations in Idaho Basilis, we also find that the other stations all have a felsic and a weaker upper crust, and intermediate and also weak lower crust. And their integrated strength is all about between 1.5 to 3.5 times 10 to the e to the 6. And here's a comparison between the two stations, Idaho Basilis, which is shown in the lower side, and L11A in the Snake River Plain in the upper side. We can see that the two different regions, they have the strength difference about 3 times stronger than in snake river plain compared with the Idaho basins. And if we do this thing for all the stations in the Intermountain Seismic Belt zone, we can get a lot of integrated strength numbers. And if we plot those integrated crust strengths with map, we get a map view like this. Okay, I plot the map view with the seismicity location of the earthquakes with magnitude 3.5 and greater happened between 1970 and 2020. And we can now see a very interesting correlation between where we see the relatively weak crust and the seismicity, especially the horseshoe geometry of the Intermountain Seismic Belt, as well as the quiet snake river plain with relatively higher strength compared with all its neighboring part. So this means if this whole region is getting a similar stress field, where do you expect the strain rate to be high? You would expect the strain rate to be high in the place where the strength is low, right? So this means you would expect those places with low strength to have more deformation. And if it has pre-existence environment to allow the earth to break, then it tends to have more seismicity. And from this map, we can also recognize several different observations. More specifically, in this place, we observe 3 weak zones: Idaho basins, Yellowstone, and the Eastern Basin Range. They all have average low strength of the crust. And the strongest crust shows up in the Great Plains, the Wyoming Craton, and the Crustal Plateau region. So if you look at the scale, here I take the log scale. So the strongest crust is about 1 times in value here, log scale. So it means it's 10 times higher strength compared with the weakest zone. And we also find that the Snake River Plains is 3 to 5 times stronger than its surrounding Idaho basins, Yellowstone, and the Basin Range. So it's the strongest part in this locality. Okay. And we conclude, okay, this perhaps explains that why Snake River Plain has very limited seismicity, because it's stronger. When you have stress, the deformation will take place in its neighboring place rather than in Snake River Plain. Although in our modeling, the Snake River Plain has higher temperature. Okay, and we also conclude that this is because of the compositional anomaly, not just because of thermally deformation, which previously studies has hypothesized. Why do we say this? So here is a comparison with and without compositional input. On the left side, I do the same rheological modeling, but I don't use my compositional model as input. Instead, I use a uniform compositional model. So everywhere here has the same upper crust composition and has the same lower crust composition. And if we take a look difference between the 2 pictures, we will see that if there's no composition involved, you will predict that the Snake River Plain and Yellowstone will be the weakest part, but not its peripheral region. And with the composition, the pattern will be more aligned with the seismicity. So here, I also conclude that it is because Snake River Plain is chemically strengthened through the, maybe through the mafic and the lower middle crust intrusion because of the hotspot track. So that is why it's seismologically quiet. And one thing to note that the seismicity in Idaho, because it's difficult to explain the seismicity in Idaho with the microplate boundary theory. But now, with the chemical information as input, we can perhaps conclude that this place has a lot of seismicity is because it's chemically weakened and allowing a higher strain rate if the stress field, if there is enough tectonic stress applied to this region. And in fact, if we look at the gravitational potential energy, people really find a high tectonic stress field in this region. So this is perhaps explain why this place has a high strain rate and as a result has a high seismicity. And by the way, one thing I want to notice that if you look at the Idaho basilis, it is so weak in this Idaho basilis that the lower crust, the middle and the lower crust is all in the plastic region. So it does not generate earthquake. This is further supported by the fact that if the deep earthquakes that happens at depths greater than 18 kilometers, they are either in the northern arm of the Intermountain Seismic Belt or in the southern arm of the ISB, but never show up in the Idaho basilis. This is because Idaho basilis has a very weak middle and lower crust. And another observation I want to draw your attention is that if we look at the pattern more carefully, you will notice that although Idaho basilis, the seismicity is in the weakest zone, but the northern arm and the southern arm of the ISB, the seismicity is distributed not in the weakest part, but at a narrow belt where the rheology varies spatially or rheology varies horizontally. This is further, it is shown more clearly if we take the horizontal gradient of the crustal gradient strength map. You will see that where the crustal strength has the highest horizontal gradient, it also has the highest seismicity. What does this mean? I do not have a interpretation for now. Actually, if you have any idea what is happening, I would very much appreciate your comments on this pattern. But my current thinking is that for an earthquake to happen, especially a relatively large earthquake to happen, you also do not want the earthquake to happen in the weakest part where the deformation can be taken over by the middle and the lower crustal flow. Actually, the lower crustal flow has been determined by many other geophysical techniques. Phil is an expert here, so I'm not going to talk a lot about it. But my point is another phenomenon that intraplate earthquake happens where the strength changes the most is also something new we just learned from this map. And if we compare the strain rate with this gradient, we can also find a very high correlation between the two patterns. So this is a very interesting finding. Okay, let me quickly wrap up what I have presented here. In the past an hour, I guide you through a journey from the seismic observation made from USArray through the chemical compositional model and into the rheological map of the Intermountain Seismic Belt. And from the new map of the Intermountain Seismic Belt, we find that the hard but chemically strong Snake River plains, which is the Yellowstone hotspot track, is surrounded by the weak zones of the Idaho Basilisk, Yellowstone, and the Eastern Basin Range. It facilitates the concentration of strain rate on its periphery rather than within the plains. And the Idaho Basilisk is chemically weakened. It allows the strain rate to take place in that area. And the main Intermountain Seismic Belt, the northern and southern arms, they reside along a boundary between the weak western US and the strong Wyoming Craton Great Plains and the Colorado Plateau, representing a belt of the changing strengths in this area. And looking forward, this work is far from being perfect. What we need to do to gain more solid conclusion is that we need to further study the uncertainty with the rheology map here. What are the uncertainties from the geotherms? We used some thermal model here, but it comes with uncertainty which is not incorporated in this study yet. We need to learn more rheological properties to crustal rocks. Now we use a very simple model to just felsic intermediate and mafic. We ignore the other impacts on the strengths like the fluid content, and they all have a profound impact on the strength profiles. And looking at the future, we also need to take strain rate as a factor to constrain the strengths, because strength is also depending on the local strain rate. We also need to look at the upper mantle rheology if we want to study the rheological profile for the whole lithosphere. And looking at the future to explain why the seismicity happens at the periphery of the weak zones, we need to do more geodynamic modeling. Okay, so to conclude my talk, I want to thank several people. I listed them here, you can read. And I want to note that the seismological work is mainly performed by my graduate student, Weisen Shen, and the work is supported by Stony Brook University, NSF, and SCAC. And thanks to Tianze for the organization of the talk, and thank you for your time and your patience for my talk. Thank you so much. Okay, so.
Okay, great. Thank you for the wonderful talk. And we're ready for questions. You can either just shout out or you can raise your hands. Oh, Gabby has a question. Gabby?
Yeah, so maybe I didn't pay attention near the beginning. But you spoke several times about the upper, middle, and lower crust. Now the crustal thickness across the continent is not the same. So how did you divide between the upper and middle and lower crust? Is it just the arbitrary depth that you defined, or?
No, the upper and the middle lower crust. Here for each location, it has different Mohel depths. So it has different crustal thickness. Specifically, when I do the thermal rheological modeling, what I do is I take my compositional model and use my compositional model to tell me what's the upper crust and what's the lower and middle crust. Some places, they have two crustal layers. For example, in Snake River Plain, beneath L11A, it only has two layers. One is upper crust with intermediate composition and one lower crust with mafic composition. How do I know where is the boundary? I use the cutoff of the intermediate to mafic composition to tell me the depth. So for example, if the average composition is goes through this boundary, intermediate mafic boundary at 12.5 kilometer, I use that. Oh, actually 50 kilometer, I'm sorry, 15 kilometer. I use that to be the boundary between the upper and the lower crust for this place. And for other places, I also define the boundaries using this method.
Oh, okay. Great. So Zeyu Jin has a question. Yes.
Great talk. Yeah, I have a question. When you use the BP and VPF ratio to distinguish different silica content.
Sure.
So what are the depth distributions of these rock samples when you distinguish different silica?
Okay.
Because I remember you make a map that to illustrate the different silica content of upper crust, intermediate crust, and lower crust.
Yes.
I'd like to know what's the depth distribution of these rock samples. When you define these three layers of the silica content, do you use these rock samples are sampled in the same depths or different depths? And you
Okay. Okay.
To inverse the silica content model for different layers.
Okay. In this place, when I do the compositional modeling, I actually don't. I don't specify whether it's upper, middle, or lower crust. Here, let me first explain the data, petrological data here. The petrological data compiled by Christensen in his famous 1996 paper and the Hanker et al. 2015 review paper contains a variety of rock samples for different depths. For example, Christensen paper has granite, amphibolite, and the granulite in his data. And Hanker, a lot of the Hanker's data is amphibolite and granulite, which usually shows up in the middle and the lower crust. But you can see that they all have the similar pattern. So no matter which depths they are, if you correct all the seismic properties to the same pressure and to the same temperature. One thing I didn't say is that those lab measurements are made at room temperature and 600 megapascal for all different rock types. So when we try to utilize this pattern to our measured seismic property, we need to correct. We made the correction of our seismic property to the same physical environment. So in this case, we didn't say, okay, this seismic property is in the upper crust, so we only want to use a subset of the rock sample. We didn't. Instead, we make the locally measured seismic property and to the room temperature and 600 megapascal and compare with all possible rock types here. If it falls here, even its upper crustal depths, but it can also have a low silica content. And when I show you here upper crystalline crust and middle crystalline crust and lower crust maps, actually what we are making here is not three layers of composition. Instead, for each location, we have a smoothly varying crustal composition. So here, when I do the upper crustal silica content, I'm taking the upper 5 kilometers of the crystalline crust for different locations and plot the map view. But one can always define different depths and plot their map view. So we do not have three clear layers of the crust. Here, I just want to show you the composition at the different depths and to see how they change with depths. Actually, they really change smoothly with depths.
Okay, thanks. Seems like your panel A and E changes abruptly, not quite smooth, as smooth as your curve looks like.
Which one? This one?
Yeah, the panel A and E.
Panel A and C?
No, the previous figure. Yeah.
This one?
No, the
What do you
left,
mean here?
the left figure.
The left figure, A and E?
Seems like it changed a little abruptly.
Oh, sure, they are different because they are composition at different depths, right? They shouldn't be the same. So for example, for station M26A, the upper crust is 50% and the lower crust is less than 50%, so they are different. And if we look at more crust compositional profiles, for instance, L11A, the upper crust composition and the lower crust composition, they are quite different. They shouldn't be the same because their seismic property change. So they do have very different composition. They are different. Upper and the lower crust, they are indeed very different. Yeah, here, I mean, they are not 3 different layers, right? But they change with depths.
Okay, great. Any more questions? All right, then in the interest of time, let's wrap up here. Let's thank Weisen again for his wonderful talk. And also want to thank everybody for taking part in this seminar series. And next week, we are going to have Professor Rebecca Fisher from Harvard University talking about her work on experiments with rocks and minerals in the Earth's deep interior. All right, thank you, everyone. See you next week.
Okay, thank you, everyone. Thank you for your time. Thanks.